Okay, welcome to this video lecture. Today we will continue on with some of the discussion we left with. We'll talk about the simple algorithm. If you recall from last time, we talked about general convection diffusion problems. We discussed the difficulty is tied to being able to quantify the pressure in the Navier-Stokes equations. We discussed central difference scheme, upwind difference schemes, beginning with a flow field that we knew, and we recognized the difficulty lies in the fact that we have to, in the momentum equations, we need to evaluate pressures at the cell faces, and in the conservation of mass in the continuity equation we need to evaluate velocities at those faces. And so then we talked about the staggered grid, which enables us to do that without having to interpolate using the standard upwind difference scheme that we talked about. So we avoid some of the issues that are tied to each of these schemes, the CDS and the UDS. So today we'll talk about how to introduce pressure into the continuity equation. So if you recall from our discussion last time, when the only place that pressure shows up is the momentum equations. At least for incompressible flows that's the case, because density now is no longer a function of pressure. Therefore pressure does not show up in the continuity equation. But as you'll see as we talk about the simple algorithm, this enables us to incorporate pressure into that continuity equation, even though we have incompressible flow. So the simple algorithm stands for the semi-implicit method for pressure-linked equations. It's a very elegant, very nice algorithm. It's also a very nice acronym. This was proposed by Patankar and Spalding in 1972. And the idea is to start with our continuity equation. We're going to substitute it into the discrete U and V momentum equations. And we're going to, in that way, sort of couple the velocity and the pressure. In each loop, what we're solving for is something called the pressure correction. And so we'll talk about how to derive this algorithm. Okay, so what we can do is we can start with just a guess for the pressure field, and we can then solve these discretized equations. That's going to give us velocities in both directions, u and v. These quantities are starred because they're not accurate. Again, we're starting with a guess for the pressure, so the velocities that we find from this matrix here are going to be, they're going to satisfy the momentum equation, but there's no way they're going to satisfy the continuity equation. So what we do is we propose corrections to each of these terms. So you'll see that our velocity without the starred or the primed quantities, our velocity by itself, this is the correct velocity. This is the velocity that we found from the previous guess or iteration of the pressure field. And each of these primed quantities in the velocities and in the pressure represent a corrector, right? Because the starred quantities are not accurate. They don't satisfy both momentum and continuity. Therefore, there's some correction that needs to take place in order for it to satisfy both. So we'll substitute these into the discrete continuity equation. And we will also require that the velocities without the primed or the starred nomenclature, they should also satisfy the momentum equations. And we're going to take the expressions that we had here, and we're going to subtract them from the equations that you see here. And the result is going to be, since all the coefficients are the same in both cases, then the result is going to be the primed quantity discretized equations that you see here at the bottom of the slide. And what we do is we are going to neglect this first term with the corrected, or the velocity correctors, and we're going to approximate these corrector velocities as a function of the pressure correctors. So we drop the additional terms. This greatly simplifies the math, and then we define these additional coefficients for the north and the east in this case. Keep in mind we'd also have these for the west and the south. But now we can express the velocity corrector in terms of the pressure corrector, so that the velocity again is a sum of the starred and the primed quantities, where the primed velocity now can be expressed in terms of the primed pressure quantities, the pressure corrector. So we'll take that, we'll look at the flow rate. So we'll look at the continuity equation. We have flow rates on all the faces in terms of primed and starred quantities, where again the accurate flow rate is going to be a sum of the starred and primed quantities. So we can take the starred velocities, so the starred flow rates, and again they're not going to satisfy the continuity equation, so if we sum all of those up, we're not going to find that this equals 0. But if we accommodate for these prime quantities, which were the corrector flow rate correctors, then if we sum all of those up, we should find that equals 0. So we're going to make substitutions for all of the primed flow rate terms that you see here with the definitions up at the top of the slide. And when we do this, now we know that we can set this equal to 0, and what we've got is flow rates, which are starred quantities, which we can compute based on velocities that are also starred quantities, which were found based on the previous either guess or iteration of the pressure field. And we've got a bunch of pressure corrector nodes that we need to solve for. So the idea is to now collect all the pressure correctors into a discretized form, and that's what you see here. So this set of discretized equations is going to be used to solve for the pressure correctors. And you'll notice this B term, which is in effect the source term, is just a sum of the starred quantities. And it's important to realize that once we iterate through this how many ever times we need to, and get to the solution that then satisfies, where the U star satisfies both the momentum equations and the continuity equations, then this B term is going to go to 0, because the corrector velocity is near 0, or very, very small. So if the pressure guess, another way to say that is that if the pressure guess happens to be correct, then U star and V star would satisfy both the continuity and the momentum, and the B term here would go to 0. So it's also important to note that if P prime equals a constant, so it doesn't, this still works. So it doesn't necessarily have to be that our pressure corrector is 0. Our B term is going to go to 0. And so we want to use that as a cutoff criteria and not the P prime, because in an incompressible flow, if we don't have pressure boundary conditions, for example, if we just have a velocity inlet and a velocity outlet, then the absolute pressure is going to be irrelevant. It's the only thing we care about is pressure differences. And so it's important to realize that B equals 0 even if this P prime does not equal 0. If P prime is constant across the whole domain, then B still is going to be 0. And we have a solution that satisfies continuity and momentum. So the solution loop is going to look something like the following. Step 1, we're going to guess our pressure and velocities. Step 2 is we're going to solve the U momentum to find this U star. And then we're going to discretize the V momentum equation to find the V star. And then we will solve the pressure corrector equation coefficients. In particular, we want to look at this B term. And once we have the pressure correctors for all of our elements, for all of our volumes, then we will apply that and update the pressure, and then go through this solution again. So step 5, we'll solve the P prime equation, and we will then apply that to all of our velocities and pressures. And then we want to take a look at these velocities to see if they satisfy continuity and momentum. And then we eventually check for convergence. If it's converged, we're done. If not, then we go back to step 2, which was starting with that new pressure field, which is now updated, resolving to find a new set of U stars and V stars, going through this whole process again. So that's the solution loop for the simple algorithm. So it's important to note here that we neglected this component shown here in blue. So in the velocity corrector equation, we dropped this out. We dropped the velocity component out, and we said that it was approximately equal to the quantity you see here in the as a pressure term. So what happens is, as we're going through this loop and we're correcting based on only on pressures, right? So what happens is it places a large burden, a numerical burden on the pressure corrector. And so what we want to do is use an under-relax approach to the pressure. So if this alpha is equal to 1, for example, then the pressure correction might be too large, and then the velocity becomes large, the pressure correction becomes even larger, velocity correction becomes even larger, and you get a solution that's going to blow up. So we're forced to have this under-relaxation constant whenever we're using the simple algorithm. And I have a Matlab example that I'll show you, and you can kind of see how this works. So keep in mind, this doesn't mean we're going to under-relax the velocity. If we do that, then we're not going to satisfy continuity. But we will under-relax the momentum equations. So I guess let's go to the Matlab example real quick. So I posted some code, and I posted a Matlab script, and then this PDF, which is it's a 1D problem. We're looking at a one-dimensional nozzle, or one-dimensional flow through a nozzle. Here's our continuity equation. Here is our momentum equation. The cross-sectional area is varying from node to node. We're just going to have a small number of nodes in this case, just to illustrate how to code this up and make it work. Density is constant everywhere, and we have a pressure outlet, a fixed condition at the pressure at node 3 and 1. So what we want to find is the velocities at A and B and the pressure at node 2. So the problem asks to formulate the discretization equations for U and P prime, find values for the velocities at A and B and the pressure at 2. So we'll start with some initial guess. So we have a velocity guess and a pressure guess. And the solution is as follows. So we start by developing the simple algorithm for this. We're doing this for each point in terms of the velocity, and for the pressure as well. Notice we're using an upwind scheme here. And here's some code. You can look through the code up in the Matlab script in more detail. But we go through this once, and we get a pressure of 25 and a velocity at A and B of equal to 1.7 and 5.8. But this is not going to satisfy the continuity equation. So then we need to look at the pressure correction equation. We only need one such equation because we only have one node that we don't know the pressure on, and that's node 2. So we develop a pressure correction equation for node 2, and this is going to give us a pressure or a correction for our velocities, and then we're going to look at those velocities and then evaluate whether they are close enough to satisfying continuity and the momentum equations is acceptable for us. And so here's the overall code to do that. In this case, I set the overall maximum iterations to 100, and then I've got a couple of different places we're checking for convergence. Here's our pressure corrector equation, and we correct the velocities, and this will kick us out at some point. And if we take a look at this code, if we just run the code as is, you notice I have a relaxation factor here somewhere. This alpha is my relaxation factor. Right now it's set to 0.5. So if you run that code with alpha 0.5, you'll see the following. So this is sort of like the convergence of these two velocities and then the pressure at the location specified previously. So if we go through enough iterations, in this case less than 40, we find a velocity of 2 and 6 and a pressure of 24. So we were, with our initial guess, we had pressure 25 and velocity 1.7 and 5.8. So we're ballpark with those, but it takes multiple loops through this algorithm to finally get velocities that again satisfy the continuity and the momentum equations. So if we take a look at the code, I just wanted to illustrate the importance of this relaxation factor. So if I set it to 0.5, I run the code, then it spits out this figure. This is the figure that was in the solution, the PDF solution. So here's my two velocities, there's my pressure. We went through 35 or so iterations. I think I have that echoed back to the screen. Yeah, so I went through 35 loops. And if I change this to something higher, then that number is going to change. We only went through 29 that time. And if we take a look at the plots, we still have what looks like smooth iteration, but if we zoom in a little bit, you'll see when we get close to the value, then we start to see some wiggly behavior. Let me run this again at 0.5. Here you see we have a nice smooth iterative approach to the value, the converged value. But again, if we start to increase this, let's go up to 0.8. So a value of when alpha is equal to 1, that means we don't have any under-relaxation. So we start to see these issues that are starting to get more severe the higher we have this correction factor. Let's go to 0.9, 0.95. You see it's almost oscillatory, and then the iteration, the small change in pressure in that case causes a large change in velocity, and then we would have to start all over again. If I take this up to 1, then the solution will blow up. Let's try 0.99 actually. Yeah, so you see the solution blows up. In other words, the change in pressure causes a change in velocity that continues to increase from iteration to iteration. So with the simple algorithm, even for this, fairly straightforward 1D system, we are forced to have an under-relaxation approach in our code. Oh, I gotta clear this, don't I? Yeah. There we go. All right, we're back to normal. So when we want to kick out of the simple algorithm, then we want to look at each loop. The velocities and pressures are updated to their new values, and then before solving the x momentum equation here, which is this matrix, we will first compute the residual, and we will evaluate that to see if it's small enough, and if it is, we'll kick ourselves out of the loop. We can do the same thing for the y momentum. For the continuity equation, all we need to do is look at the magnitude of that b vector in the pressure correction equations. But when you run a simulation like in STAR or some other commercial package, then you'll see a plot of the residuals as a function of your iteration number, and this is exactly what it's doing. It's calculating that residual for each of the three momentums and continuity, and we do this separately because this is what's called a sequential algorithm. So we solve these things sequentially. So we solve them separately. The term is a segregated flow solver. There are also coupled flow solver options, at least in STAR I know there is. And they are solving the matrix that you see here. So this represents a large matrix. We've got the U. We have U at all our nodes. We have V at all our nodes, and then we have pressure at all our nodes. We've got the source terms in each of these. This is 0 because this bottom equation represents our continuity equation. So we don't have pressure built into that. That's why this section here is blank. All these lines here represent non-zero entities in our matrix, in our A matrix, our coefficient matrix. So you see in the U momentum, we've got the point P, we've got its east and west neighbors, then we've got our north and south neighbors here. It's not going to be a function of our our V velocity, but there will be pressures at least in two locations, one at the current node, and one maybe downwind, one upwind. But you have something similar for V, and then again our continuity equation here on the bottom. So this is what it would look like, this banded sub-matrix and matrices in this larger matrix. And this is what it would look like if we had a 2D mesh, staggered structured grid. So the coupled flow solver is basically just solving this matrix as a single entity. It's not calculating these things separately and then substituting the updated values into the next one, etc., like we just discussed with the simple. A couple additional solvers that you want to be familiar with. One is called simple C. There's also simple R or simpler, but it's not quite as popular these days. Simple C or simple corrected. It uses an approximation for the neighbor velocity terms. So the quantity that we got rid of in the velocity corrector equation, we don't get rid of it altogether. We have some approximation that we use in place of that. So it still makes the algebra a little easier, but we don't neglect it altogether. And because we don't neglect it, now we don't need to worry about under-relaxation. And as a result of that, it's faster convergence. Another one is a PISO, this pressure implicit with the splitting operator. So it also does not need under-relaxation. It has additional corrector stages that are used to address the slow convergence, and it does quite well in transient cases compared to the transient simple, and it also does well with if you have cells with a high aspect ratio or high skew. Okay, so next time we'll talk about, or I'll provide some videos for each of your softwares that you've chosen, and we'll start diving into what those are doing behind the black box. All right, we'll see you next time.